The Boeing Starliner, officially designated the CST-100 Starliner, is a spacecraft developed under NASA's Commercial Crew Program with the primary goal of transporting astronauts and cargo to and from low Earth orbit, particularly the International Space Station or the ISS. This spacecraft represents a significant advancement in commercial spaceflight capabilities and aims to provide safe, reliable, and cost-effective transportation for NASA and other commercial missions. The Starliner is engineered to accommodate up to 7 passengers or a combination of crew and cargo with a specific configuration for NASA missions that allow for 4 NASA-sponsored crew members along with essential scientific research. The spacecraft features an innovative wellness structure which enhances safety by eliminating structural risks associated with traditional welding methods. This design not only minimizes production time, but also contributes to the spacecraft's reusability, and this allows it to be flown multiple times with a turnaround of approximately 6 months. The Starliner is a testament to Boeing's commitment to advancing human spaceflight capabilities through innovative engineering and design. Boeing's vision for the Starliner extends beyond merely fulfilling NASA's immediate needs. It aims to establish a long-term presence in the commercial space sector by providing reliable crew transportation services that can cater to various customers, including international space agencies and private enterprises. The spacecraft is designed with versatility in mind, allowing it to adapt to different mission profiles, whether that involves transporting astronauts for ISS missions or conducting private missions for commercial customers looking to conduct research or tourism in a low Earth orbit. This flexibility is crucial as the demand for space access continues to grow in both government and commercial sectors. As such, the Starliner not only serves as a vehicle for human spaceflight, but also symbolizes Boeing's strategic pivot towards embracing the burgeoning commercial space market. Boeing began developing the CST-100 Starliner in 2010 as a part of NASA's Commercial Crew Development Program. The spacecraft's design draws upon Boeing's extensive experience, and this is with NASA's Apollo, the space shuttle, as well as ISS programs, and this goes to the company's expertise in commercial aviation. The Starliner is designed to be compatible with multiple launch vehicles including the United Launch Alliance Atlas V, providing flexibility and redundancy in launch options. This compatibility ensures that Boeing can adapt its launch strategy based on customer requirements and market conditions, thereby enhancing its competitive edge. The spacecraft's capsule architecture is also reminiscent of the Apollo spacecraft, featuring a gumdrop shaped crew module and a cylindrical service module. However, it incorporates numerous technological advancements and modern design features that distinguish this from its predecessors. For instance, the Starliner employs advanced avionics systems that allow for automated flight operations while retaining manual control capabilities for astronauts during critical phases of flight. This dual mode operation enhances safety by allowing astronauts to intervene if necessary while benefiting from automation during routine operations. The Starliner's construction employs an innovative weldless design, which reduces mass while improving structural integrity. This approach eliminates the structural risks associated with traditional welding methods while enhancing overall safety and integrity. The capsule's heat shield employs Boeing proprietary lightweight ablator, or BLA for short, and this material provides a robust thermal protection during atmospheric re-entry. This heat shield is designed to withstand temperatures exceeding 3,000 degrees Fahrenheit during re-entry into Earth's atmosphere, ensuring that the crew remains safe throughout the descent process. Additionally, the materials and construction contributes to weight savings without compromising structural strength. One of the most notable features of the Starliner is its reusability. The spacecraft is designed to be used up to 10 times, with a turnaround time of approximately 6 months between the missions. This reusability is expected to significantly reduce the cost of access to space and enable more frequent crewed missions to the ISS and other low Earth orbit destinations. Furthermore, the Starliner features an advanced environmental control and life support system that maintains cabin temperature, humidity, air quality, and includes a waste management capability. This system ensures that astronauts can live and work comfortably during their missions while maintaining their health and safety. The Starliner is equipped with cutting-edge technology that enhances both its operational capabilities and safety features. It includes a pusher abort system, which ensures safe crew escape during launch as well as ascent phases. This system allows for immediate separation of the crew module from the service module in case of an emergency during launch. The pusher abort system utilizes solid rocket motors mounted on top of the crew module that can quickly propel it away from the launch vehicle in case of an anomaly during ascent. This capability is crucial for astronaut safety and reflects Boeing's commitment to designing systems that prioritize human life above all else. The spacecraft's propulsion system consists of 64 strategically positioned jets that allow for precise navigation and fault tolerance. If one jet fails, others can compensate to maintain the spacecraft's trajectory. That is what is meant by fault tolerance. These jets are powered by hypergolic propellers, specifically monomethylhydrazine, MMH for short. This is the name of the fuel, and this is used as fuel as well as nitrogen tetroxide N2O4 as an oxidizer, which allows for immediate ignition upon contact without requiring an external ignition source. This level of redundancy is crucial for ensuring reliability during critical phases of flight. Furthermore, the Starliner operates with a high degree of autonomy, and its advanced guidance navigation as well as control system enables it to autonomously navigate to and dock with the ISS using a combination of GPS, inertial measurement units, IMUs for short, and optical sensors. The docking process is facilitated by the NASA Docking System, or NDS for short, adapter compatible with the International Docking System on the ISS. This docking system was modified prior to recent test flights to include a hinged re-entry cover below the expendable nose cone for additional protection during atmospheric re-entry. The NDS provides a standardized interface that allows different spacecrafts from various manufacturers to dock seamlessly with each other while ensuring safety protocols are adhered to during and both approach as well as docking maneuvers. The interior design of the CST-100 Starliner emphasizes crew comfort and safety, a critical consideration given that astronauts may spend extended periods aboard during missions. It features ergonomic seats that are individually adjustable to accommodate crew members of varying sizes while ensuring optimal support during launch and landing phases. These seats are designed to absorb forces experienced during launch, upwards of 5 G forces, and landing impacts upwards of 6 G forces, similar to like fighter pilots, how they experience G forces when making extreme turns up and down. And these minimize injury risk through advanced cushioning materials engineered specifically for aerospace applications. The cockpit includes touchscreen displays that provide real-time data on vehicle status while allowing crew members easy access to critical systems without overwhelming them with information overload. Each display can be customized according to individual preferences or mission requirements, ensuring that astronauts have all necessary information at their fingertips, while maintaining focus on their primary tasks. In addition to comfort features, safety measures are paramount in the Starliner's design. The spacecraft includes an automated emergency detection system that continuously monitors vehicle parameters throughout flight for any anomalies or malfunctions detected during launch or ascent phases. And the system can signal an abort command if necessary for crew safety. Furthermore, each seat is equipped with individual oxygen masks connected directly to onboard life support systems should cabin pressure drop unexpectedly, and this ensures that astronauts have immediate access to breathable air, even in emergencies. The cabin layout has been carefully considered not only for functionality, but also for psychological well being. Large windows provide natural light, while offering stunning views of Earth below, a feature intended to enhance morale among astronauts on long-duration missions aboard Starliner. Additionally, thoughtful storage solutions have been integrated into the cabin design so that personal items can be stowed securely while still being easily accessible when needed. Boeing has conducted extensive testing campaigns leading up to the Starliner's operational missions. Each phase was meticulously planned out in order to validate every aspect of performance before embarking on crewed flights into orbit. The initial uncrewed flight test in December 2019 faced challenges primarily due to software glitches preventing successful docking with the International Space Station. However, subsequent tests have yielded better results demonstrating improvements made since then through focusing around addressing earlier shortcomings. And this identified that during previous evaluations that there needed to be iterative redesign processes. And this is what led them to success. So for instance, in May 2022, the Orbital Flight Test 2, OFT number 2 for short, Starliner successfully docked with the ISS, but encouraged propulsion, and this encountered propulsion issues upon return when the thrusters failed due to overheating, a situation exacerbated by their design placement within heat-retaining shelters or on exterior surfaces. These findings provided valuable insights into how thermal management strategies can be improved moving forward, ultimately leading toward enhanced reliability across future operational flights scheduled later this decade. The recent Crew Flight Test (CFT), launched on June 5th, 2024, marked a pivotal moment for Boeing as it was their first crewed mission aboard Starliner. Despite achieving several mission objectives, including autonomous docking with the ISS, the CFT faced significant challenges when multiple helium leaks were detected within propulsion systems shortly after launch. These issues led NASA officials, including Administrator Bill Nelson, to decide against returning astronauts Barry Butch Wilmore and Sunita Suni Williams aboard Starliner due to safety concerns regarding thruster performances during reentry. Now, following its uncrewed return on September 6, 2024, after completing mission objectives successfully, landing safely in New Mexico, Boeing began analyzing data that was collected from CFT before certifying Starliner regular crewed flights moving forward. This thorough evaluation process will involve assessing all aspects of related performance metrics gathered throughout the entire duration of each test campaign conducted thus far. The economic impact of developing Starliner extends beyond Boeing itself. Over 425 suppliers across 37 states contributed significantly towards its creation, from small businesses providing specialized components like valves or electronics, up through major aerospace contractors involved in manufacturing larger assemblies, such as fuselage sections or avionics suits, demonstrating how collaborative efforts across industries can yield groundbreaking advancements within space exploration sectors. Boeing's partnership with NASA has also been instrumental in shaping policies surrounding commercial spaceflight operations post-Space Shuttle era, following shuttle program retirement in 2011 when reliance on Russian Soyuz spacecraft became necessary, transporting astronauts until domestic capabilities could be restored through initiatives like Commercial Crew Program or CCP. By fostering relationships between government entities like NASA alongside private industry players committed towards advancing human spaceflight capabilities, Boeing has positioned itself at the forefront of innovation-driven sectors, which are poised for growth amid increasing global interest surrounding exploration beyond our planet's atmosphere. Moreover, the financial implications stemming from delays experienced throughout the development cycle cannot be understated. The initial contract, awarded worth approximately $4 billion, has since ballooned due to unforeseen complications arising from various stages testing campaigns, resulting in estimated losses nearing $1 billion thus far. These challenges raise questions about the viability of future projects undertaken by companies unless they can effectively address issues hindering progress while simultaneously maintaining competitive edge against rivals such as SpaceX, who continue to push innovation faster than ever before. Looking ahead at future missions planned under NASA's Commercial Crew Program will require rigorous evaluations based upon findings gleaned from ongoing testing campaigns involving both uncrewed flights as well as eventual certification processes that are necessary before operational launches commence again later this decade. The next anticipated mission for the Starliner is tentatively scheduled for August 2025, which is a milestone known as Starliner 1, which will be its first operational crewed flight following successful completion of all test objectives laid out prior. As part of this program aimed to ensure continuous human presence aboard the ISS, NASA has ordered 6 crew rotation missions aboard Starliner intended not only to bolster international partnerships but also facilitate scientific research opportunities critical towards understanding long duration spaceflight effects upon human physiology. With these commitments underscoring the importance of maintaining multiple American companies capable of safely transporting astronauts, a critical aspect of future exploration endeavors beyond low Earth orbit. In addition, Boeing plans to leverage insights gained through these upcoming operational flights to inform future design enhancements made across entire fleet vehicles produced under Commercial Crew Program umbrella, ensuring continued success in meeting demands of the evolving industry landscape, characterized by rapid technological advancements occurring regularly within the aerospace sector today. In conclusion, while both SpaceX and Boeing are integral players within today's commercial space industry, their trajectories reflect fundamentally different philosophies regarding innovation, risk management, and long term goals. Elon Musk's vision for SpaceX emphasizes aggressive pursuit, interplanetary colonization, seeks not just access but sustainability across multiple worlds. And this is a perspective that inspires both employees at his company and enthusiasts worldwide eager for humanity's next great leap into the cosmos. Conversely, Boeing must confront its challenges head on if it hopes to remain relevant amid fierce competition from agile startups such as SpaceX, who are reshaping our understanding of human exploration beyond Earth's atmosphere. Ultimately, the story unfolding between these two giants serves as an exciting chapter within humanity's quest towards unlocking mysteries beyond our planet while ensuring we do safely along every step taken into uncharted frontiers.